As functional programmers, we figured out a better way to do data transformation. No longer do we do these manual for loops where we have to think about I and j and temp and all of these variables that are constantly changing their values over time. No longer are we trying to look at these nested for loops to try to figure out what in the world our code is doing. Instead, we have this clean way. We have these functions like filter, map, reduce, partition, zip with. We have a clean, clear way of doing data transformation. And so if we've really made something better, we have to ask, in what way is it better? Like, what have we gained? And these are the sorts of things that we talk about. We have more readable code, right? And so maybe some of you are saying, like, no, it's not more readable. I've read people's functional code, and it's atrocious. It's ugly. But like, sometimes, when we first see it, it is hard to read. But after we've learned these things, there's these patterns that we've been trying to say in our for loops. There are these patterns that we've been wanting to talk about, and now we've given it a name. It's map. It's filter. It's partition. And so in a lot of ways, it is more readable. We also have this declarative approach. When I say map, I don't have to think about how the map is going on. It could be lazy. It could be strict. It could be doing it in parallel. We could have intermediate data structures, or we could have deforestation. Our compiler can be smart about this, because we're not telling the computer step by step what to do. We're saying what we want. And so we get to focus on the what and not the how. Or at least this is what we tell ourselves. We tell ourselves we've really come up with this better way. But today I want to question, is it that much better? Right? Have we really made a better approach to data transformation? Let's look at some code just some fake code to think about this. So here I have the stereotypical pipeline, right? Maybe you're not a pipeline person. Maybe you think pipelines are overrated, but think about your ideal functional code that does data transformation. Think about it in your head, or look at this one on the slide and ask some questions about it. Like, what is the shape of my input? By looking at this, we really can't tell. What's the shape of my output? Something about foo and bar. We have no way of knowing. And some of you right now, because I'm at Strangeloop, are thinking, yeah, that's because you're using Clojure. If you use Haskell like you should, you would know the types, right? You know the type of the input, you'd know the type of the output, and you'd know the types all the way down. And that's true. Types are great. I'm not here to talk bad about types, but that's not what I'm talking about, right? When we look at our code, if we've told ourselves we have a declarative approach, then shouldn't our code reflect the problem that we're solving? Shouldn't our code reflect the problem that we're solving? And it doesn't. It doesn't look like it. In the end, if there's a bug in this code, I have to think about step by step how this code is accomplishing it, and I have to think, where could that value come in this pipeline? And this isn't simple pipeline. Maybe it's actually nested. And maybe if you wrote it, you can figure it out. But if your coworker did, there's no way you're figuring that out. In the end, we still end up playing computer in our head. We are still thinking about step by step how the computer is accomplishing our task. And so that's what we're going to start with today. We're going to be talking about Meander, which is a Clojure library made for doing declarative data transformation. And so we're going to talk about Meander and its philosophy, how it views programming as data transformation. Then in this section, we're going to be looking at some practical examples of realistic data transformation. They have to fit on my slides, so they're not going to be the things that you actually do at work, but they're going to be analogs. Then we're going to talk about how we can take this approach further with Meander. I'm going to show these kind of silly little problems that you might think, well, yeah, but my problem is much more complicated than that. And I have a 40-minute talk to try to show you all of the things that Meander can do. No, I can't do that. So we're just going to just look at, look, there's more features than what I can show you in 40 minutes. Then finally, we're going to look at the future. And we're going to look at Meander's near-term future, the things that we have planned for it, the ways that we can extend it. But we're also going to look at the distant future. What if we took the idea of coding is just data transformation seriously? What if we extended this philosophy that Meander as a library has had to an actual programming language? What features will we get? What benefits will we have? Maybe we could actually have a declarative language that can do the things that we want to do. So before we dive into all that, just a little bit of introduction. My name's Jimmy. I work for AdZerk. We provide an API that lets you build an ad server to do a server-side ad platform. We're hiring. We're also sponsors of StrangeLoop. So if you're interested, come talk to me. We have a booth. Find people who work at AdZerk. Reach out. So Meander. Meander is this Clojure library. It actually got accepted into Clojure Together, which is a great nonprofit that's raising money for people to support open source software. And it's being actively worked on. But one thing I really want to call out here is that it borrows heavily from this concept called term rewriting. So we're really indebted to these great languages like Stratego, Mod, Pure, or maybe one that you might have heard of like Mathematica, that have pioneered this idea of term rewriting and applied it in a lot of ways. And we've taken a lot of inspiration from them. I wanted to talk about this in my talk, but there just isn't time. So I really just want to say there's some prior art here, but we've taken this and moved it to more practical, I don't want to say practical, more everyday things. Things that I'm doing in my day job that you're probably doing in your day job. But I want to say for sure that I am not the creator of Meander. This man here, who I know is Falcon, so that's what I'm going to call him. Falcon is the creator of Meander. Falcon is a fantastic software engineer that I had the pleasure of working with, who's worked tirelessly on Meander, who is really thinks about how we should relate to our code and what our code should look like. So I am greatly indebted to Falcon, who unfortunately couldn't make it to StrangeLoop this year. So let's dive in. Let's start with the hello world problem. Here's our hello world problem statement. On the left, we have input. On the right, we have output. This is really, really simple. And right now, you're probably thinking how you would write this code in your language. And it would be great code because it's a hello world problem. Every language should be able to do this easily, right? So we're going to talk about how we approach this sort of problem with Meander. Meander is fundamentally about pattern matching. So what we're going to do is we're going to take our data, and we're going to replace some things with variables. So here, I've just taken our input and replaced all the bits I care about with a variable. So our variables here that start with a question mark are called logic variables. And they're just going to match on whatever value they find. And then we can propagate these over to our output. And so now we have input and output. We have our variables matched up. And if I turn this just vertically and wrap it in this function called match, we have the Meander solution to this problem. Now, this isn't very exciting. This is a hello world example. And your language, the code wouldn't look that different. And in fact, because you're at StrangeLoop, you're like, did I choose the wrong talk? Is this really a talk about pattern matching? I know what pattern matching is. I don't need to talk about pattern matching. And I'm sorry to say, yes, this is a talk about pattern matching, but it's pattern matching on steroids. It asks the question, what if pattern matching were the fundamental unit? Another way of thinking about it is, I'm a Clojure developer. So I really enjoy the rich data literals that Clojure has. I think it lets me talk about data directly. But what if I had data transformation literals? What if I could directly talk about how data is transforming from data to data, how it's relating to itself? And that's what Meander's about. So to understand that, we're going to go through a little bit of an extended example. Right? And to just give a little background, we have I have to come up with a good relatable example. So I just picked an RPG. We have some game, right? Like Pathfinder, D&D, whatever RPG you want, and we're going to have some players. They're going to have weapons, and we're going to look at how we can take this data structure. We're going to start with the data structure definition. We'll look at what we want to do to this data structure, and we'll look at the Meander code for doing it. And we'll see some of the power that underlies this stuff. So here's our data structure in its entirety, but this is a lot of text on the slide, so we're going to break it down. Right? So here's what we have. We have 4 parts that we really care about. We have our players, we have our weapons, we have the stats. These are the stats of the weapons, and we have a set of third-party weapons. All right? So here's our players. Right? So we have 3 players. We have Jimmer, we have Sir Will, and we have Dalgrith. We have a class. Each player has a class, so we have warrior, knight, and rogue. All right, pretty simple, pretty basic players. Could have had a lot more, but this is a talk. So here we have our weapons. So we have the name of the weapon, and then we have the allowed classes. For any of you who aren't Clojurists, this hash curly brace is a set. We have a set of values here. So we have a warrior and a knight. And these allowed classes are, the only people who can use this weapon, right? So these are the classes that can use this weapon. And then we also have the standard upgrade. Every weapon will have a standard upgrade. And then you'll see in stats that we have more upgrades, okay? So here's our stats. Our stats are just a map from weapon name to their stats. You're almost never wanting to just loop over stats and just list stats. You want to look up stats. So here's our stats. And you'll see here that weapons can have this additional upgrade, and they also have an attack power. And then finally, the last part of our data definition is this third-party weapons. We have the unbeatable weapon, as third-party weapons always seem to be. So here is our requirements, right? We want to find all the valid player weapon combinations. Okay, so there's these allowed classes, and each player has a class, and we need to make sure that these things match up, right? We want to find all the valid player weapon combinations. We need the name. Once we do that, we need the name of the player, the name of the weapon, the class of the player, the attack power, and all the upgrades. That's the standard upgrades and those that are in stats. And right now, well, actually, let's look at the output first. So here's the output. Given our data set, this is what we should get. You can see here Jimmer has 2 different weapons that he could use, the long sword and the short sword, whereas the other 2 only have 1. And you can see we gathered up all those upgrades. Right? Now, right now, you're a programmer. You're thinking, OK, I know how to do this. And you would probably be thinking about some maps and filters and whatever, right? And you have to think, OK, do I start with the players and look for all the weapons? Do I start with the weapons and look for all the players? Do I first filter out the third-party weapons? And you can do it. It's not hard. And in fact, I wrote the code in Clojure. Here's my Clojure code. It's really bad code because I intentionally made as many anonymous functions as I could so that it wouldn't take longer on the slide and you would think I was cheating. But there's stuff that I just don't like about this. The output's actually not too bad. You can kind of see it. And I've done some unnecessary destructuring here that I really didn't need to do, but I kind of like to be able to see what keys I'm going to be caring about. But ultimately, if you didn't write this, it is not immediately apparent. What is our input? What is our output? What does it look like? And I want you to contrast this with the Meander code. And here it is. So you don't know Meander very well, but immediately you can start seeing our input and output. We care about the players. We care about the weapons. We care about the stats and third party. And then ultimately, we're going to get out a name, weapon, class, attack power, and upgrades. And so this already, even if you don't know it, you can start seeing what the data looks like. And so I want to walk through this and tell you how this is working, or at least explain what's going on here. So we start with search. So search is a Meander function that allows us to get multiple answers out. So we're giving it a pattern to match on, and it's going to find all instances of our pattern that match. So here we have players, and we're going to say we have our game info. That's that big data structure. We have players, and we're going to say we're going to scan the players. All right, so scan just says, given a collection, find anything that matches this pattern. Okay, so we're going to find a map that has a name and a class, and we're going to assign question mark name and question mark class. We're going to do the exact same thing for our weapons. We're going to scan through our weapons, and we're going to have the name of the weapon. We're going to say that's question mark weapon, and then we're going to do these allowed classes. And this is where it gets interesting. We have this hash, this set, question mark class, where we've already defined question mark class above. And so what we're doing here is we're joining across these data structures. We're saying whatever you found in the players, whatever class it was, better be in the set of allowed classes. So now we can do this join. And then we have, underneath that, the standard upgrade. And we have this new variable type called a memory variable. And it says bang upgrades. And what memory variables do is they remember anything that they match on. So they get added to a list of values. Okay, we can move on. Now we can go into our stats. Well, look, our stats is a lookup. So we have this weapon. Well, we've already defined weapon up above. So again, we're joining across these, and we're doing a constant time lookup through this join. Then we have the attack power, and we're saving that off. And then we have our upgrades. And here, that's memory variable comes into real play. We say bang up. We say, I'm looking for a vector, a list of things, right? And I say bang upgrades. It's going to match. And then this dot, dot, dot means repeat 0 more times. Basically, find all the things that are in here and just save them all off. I want to keep them all. And then finally, we get to third party. And we just say, and it better not match the pattern that our weapon is in the set of third-party weapons. And this is weird. This is a very different approach. And right now, you have a lot of skepticism about, like, why? Like, no, this isn't better. I like my map filter and reduce. And, like, that's OK. Or maybe, like, this is going to be too slow. Right? Like, probably that's what you're thinking. And we'll talk about that. But I think this really gets at the data transformation that we've been trying to do. We have our output now, very directly. We have a way of doing this. And I found when I went to write this code, all I did was copy and paste my data structures and change little bits. It became really obvious. I didn't have to think, do I start with the weapons? Do I start with the thing? I just thought about my data and described the relationships between it. And what I found is when I refactor this code, it also becomes really obvious. If, for example, let's say I have some bad data, and sometimes the player's name is nil, and when it is, like, it's just bad and I don't want it, I can just put and not nil up at that name. I don't have to add another filter and figure out where it should go in the pipeline. I don't have to restructure my code in any way to change my input and output. But of course, this is just one example. Let's look at some other ones. So here's, I grabbed down a random JSON file from a game called Pixelmon. So it's actually a mod for Minecraft that lets you play Pokemon in Minecraft. And they have this like ridiculous JSON file that has item templates. And there's all the possible items in the game. And some of those items are Pokemon. But the way they do them is they just have Pokemon settings. And so what this actually does is I pull out all the rare Pokemon. So if they have a rarity, this is just their data structure. If they have a rarity, it's some value, it's some string. If they don't, it's null, right? And so I pull out all the rare Pokemon. I pull out their Pokemon ID, which is actually just their name. And then I pull out their form, because only certain forms, and I pull out their stats. And then here, I'm using another feature of Meander called substitute, where I can say, I'm remembering all of these, and then I can say, hey, make me a list of all of these. For every single time you see a Pokemon, one form, one rarity, one stats, keep doing that over and over again. Make these maps. And so I just took an arbitrary data structure, and now I can very declaratively say, give me all the rare Pokemon. And maybe I only want the rare Pokemon who are at their final evolution. There's things in that. There's all sorts of other data in here that I've just ignored. But I could add these, and they would become really obvious how to add them. Or maybe we want a little bit more programmatic example, not Pokemon. So here, Meander actually works in Clojure script as well as Clojure. So I pulled in a JSON library, or a JavaScript library that lets me parse JavaScript. And I can actually start doing things on the AST. So here, JavaScript, I love JavaScript. But come on, like there's like at least three ways or like 4 ways to define a function, right? And so this one actually goes and finds all my functions, no matter how nested they are, no matter how many ifs they're wrapped in or whatever, right? This finds all my named functions and finds what line number and character they're at. And so this could be function, name, parentheses, or it could be var or let or const, name equals, and then an arrow function or a regular function. I'm going and mapping on the AST. And so I'm finding every single function and their location, their name and their location. And if you look at the AST, this is just the data structure that they defined for the AST. I didn't have to think about how do I recurse through the tree. I didn't have to think about any of this stuff. It becomes directly obvious. And then I pulled out another one. So here's Reddit. So if you go to reddit.com/.json, at least on old Reddit, I don't use new Reddit. On old Reddit, you can go to that. I don't know if it works on new Reddit, and they'll give you this like crazy data structure of all the things that are on that page, right? So this is pulling down all the posts that have an image, and then it's outputting HTML. So we just get a big HTML page of all of the posts that have images, their link, their title, and their source image. So there's a few things that I could call out. So like, this is their structure, so it's a little weird. They just have this like list of images, and then the first one, it's always the first one, has source, and then I'm saying this ampersand underscore just means like, and all that the rest of that stuff, ignore it. I don't care about whatever else is in there. And then here at the bottom, I'm using substitute again to be able to do this repeat operator. And what this ... will do, it says repeat all the way up until you find a dot. So the dot's where I stop. I have this outward container, and then I have all the elements inside of it. And there's a lot more that you can do with all of this. In fact, we have a ton of operators that I can't talk about. And I've mentioned some of these here. But you can also define your own custom operators. In fact, most of these are not primitive operators. They're defined in terms of our more primitive operators, and we dog food our own extension method. But maybe you have a way that you want to talk about your data. You want a declarative approach to doing this, and you can write your own operators just by defining your own matches and then use them. You can package them up as a library. There's nothing special about these operators. You can do the same exact things. They can use arbitrary Clojure coding and make this work. But still, as much as these examples have been interesting, like, there's a lot of things that I can't do with what you've shown me so far, right? Like, come on. Like, maybe I have a recursive data structure. Where's your God now? Right? So we can do that, right? We can do some recursive data structures. So, there's actually a couple ways. And I can only just touch on this. We don't have a lot of time to get into how all this works and what the trade-offs are. There's trade-offs here. But let's just look at one really simplistic example, right? So here we have a little bit of code going on, but we're getting rid of all the zeros in addition. Okay. So if you have anything plus 0 or 0 plus anything, it's just that thing. So here I've just defined a pattern match, this rewrite that says if it's x plus 0, then just it's x. If it's 0 plus x, then it's x. And what I'm doing now is I'm using strategies. So when you define a rewrite rule, you can say, like, hey, I'm actually going to have this tree of things, and I want you to have a strategy for how you tackle doing this rewrite recursively through the tree, right? So here what I'm doing is I'm saying this first attempt strategy. Attempt says try to do the pattern match, and if you fail, just return me back what you had originally, right? So maybe it's just 2 plus 3. Well, that doesn't match either of our patterns, so we just return back 2 plus 3. Or maybe, and then we have bottom up. So bottom up says if you give me a tree structure, start at the smallest elements and then work your way up, right? And then finally, I have this until equals, which I didn't actually need, I'm pretty sure, but I didn't write a proof for it, so maybe I did. So I have this until equals, which just says keep doing this thing until nothing changes, right? Until the old value equals the new value. And so here you can see that we can simplify this addition. But some of you are like, that's cheating. All you did was make function combinators. That's not a declarative approach to anything. I can write function combinators. So we actually have some ways of doing this without cheating and going out to the Clojure world. We actually have a way of talking about recursive pattern matching. And right now it's a little limited, and this example is actually more verbose than it needs to be, because the less verbose one is more mind-bendy. So I made it more verbose. But here's an example where we can actually do this very similar thing. Technically, these will reproduce different results and different things. Anyways, it's basically the same. So here we have this with operator. And with actually allows us to do recursive pattern matching. And right now, it's a little limited because you can't pass it parameters. And I'm not going to explain exactly how this code works because I have no idea. I wrote it, and there's a lot going on, but it's really cool, and we could actually have done things like, actually practical, not just removing zeros, like write a hiccup parser that produces HTML using this sort of thing, and the performance isn't quite there, but it's getting there. And so, in fact, that's what we're going to talk about next. Like, everyone's thinking, isn't this going to be slow? Yeah, it's cool. You've done some stuff. But no one does this for a good reason. This is slow. I've used Prolog once. It just stopped. I did something, and then it just sat there in an infinite loop forever. And that's all you're talking about. We've been down this territory. There's a reason we don't do it. And so, let's talk about that. First off, this is not Prolog, and it is deterministic. You're not going to just sit there forever. But is Meander fast? Well, Meander is often slower than the code I'm going to write by hand. It's just reality. Some of that is because we're a little bit more strict than Clojure is. So if you say you want a map, we're going to check that it's a map before we do something and not just do it and blow up, right? We're going to say is it a map? Oh, it's not. We don't match. So some of that is just predicate overhead. But oftentimes, we're kind of bad at generating code that's fast. But I've never personally had it be too slow for the sort of problem I'm solving. And if I have, maybe once, I've gone and changed a line of code in our compiler, and it makes it a lot better. But it's going to continue to get faster because we haven't been focused on this. We've been focusing on the problems that you want to solve. We've been focusing on the data that you care about and giving you a way to talk about it directly. A way that kind of looks like how you'd talk about it on the whiteboard. We want it to be clear what's going on. I can send Meander code to somebody else who doesn't know my problem, and they should be able to understand what's going on because they can see the data structure. So that's what we've been focused on. And in order to accomplish all this, we've actually, mostly Falcon, but a little bit me, have put in a lot of work, right? Under the hood, we got a lot going on. We got a parser. We got an expander, so those custom operators that you can make, they're kind of like a little macro expansion setup. We have this matrix-based IR, which if you've ever looked at pattern matching, that's a pretty common way of doing it. We're not using it as well as we could. We have a second-level IR that's intermediate representation, so that's a little closer to like the code that we put out at the end. This one actually will probably change pretty soon. We do some dead code elimination, so by default, if we can tell that actually no, we didn't need to do that, we'll get rid of a lot of the code. We do some optimization, so we handle some common cases, like literals versus actually having to look at stuff. And then we do some simple type inference. I wrote it. It's not actually type inference, but it kind of is, and it helps us with dead code elimination, because if you pass me a map and you have another pattern that's about vectors, well, I know it's not a vector. I just get rid of that code. If you I can actually just only generate code that says, nope, you're wrong. So that's fun. And then we have code generation, right? And so we have all of this mechanism underlying everything that lets us optimize, that lets us be a lot more efficient. And we've kind of written our own little language, kind of a Lisp curse thing, right? It's fun though. All right. So what about the near-term future? So right now our error messages suck. If your pattern doesn't match, we say your pattern doesn't match, which is true. But we have all sorts of data in our AST and stuff. We keep what you had, the original form. Even if you expand out, we know the original form, not just your expanded version. We can do a lot better, and it's really just propagating some things. I'm hoping that we can get Elm-style error messages at some point. I think we can. I think it's doable. We're going to make faster code, right? Right now, we have a lot of things that we know are just bad. I took something from polynomial time to constant time. We have things like that where it's no, we just don't need to be doing that. There's no reason. We're trying to guarantee that we're going to give you back the result right now instead of focusing on speed. And now we're moving towards caring about the speed. We want to have less code generated. So if you're in the Clojure community, if you ever use core match, if you do the wrong match, you might get this code is too big for the JVM message. I've never done that with Meander. I'm sure someone can go out there and do it right now. But I've never accidentally done that. We're going to have more powerful recursive matches. So width right now is a really interesting construct, but it can't take parameters. And if it could, we could do some really cool stuff. So we're going to be doing that. And then update in place, by this I don't mean mutation. But again, if you're in the Clojure community, Spectre might come to mind when you're thinking about this. And it's all about I can find some super nested thing and increment a number. Meander's not aimed at that right now. We don't really have a great way of doing that. We think that most of our data transformation is actually from this structure to a totally different, or a fairly different structure. And the only reason we're updating things where we find them is because it's easier with our tooling. We actually could just do the transformation as part of that step. But there are use cases for this, and we want to add support for it, and we can. And then finally, just more user extensibility. Anything that we can add, you should be able to add. There's no reason that there's some core primitives, but ultimately, you should be able to make things faster. You should be able to add more extensions. You should be able to add more operators. Whatever you want, we want you to be able to add it yourself. And I could just end the talk here and just say, this is Meander, go use it, yay. But I want to talk about the distant future. I am a pie-in-the-sky kind of person. I don't really care about practicality that much. I care about interesting, beautiful code. And so let's talk about where this can go. Right? Where can this go? So this is what I'm going to say. I think we could actually have truly data-oriented programming if we took this seriously. Term rewriting is kind of this inspiration that we've based the stuff on. It's kind of the semantics of how Meander is working under the hood. And if we accepted that, we could have truly data-oriented programming in a way that us Lisp programmers like to claim we already do. All right, so but we don't. And in fact, we can see this, like at least in Clojure, and I think most lists have this thing. Let's say you have a function, a lambda, and you evaluate it. What do you get back? You get back this opaque token. Yeah, you can wrap it in a function. You could pass it to a function. You have higher order functions. You can put it in a data structure. But can you look inside the function and see what's going on? And this might seem like an arbitrary distinction, but if you've used libraries like core async, this really has real ramifications where we can't pass that lambda boundary. But I think it's more than just this. If we just solved this problem, that wouldn't be that interesting. When we talk about code is data, data is code, what do we mean? We mean the text of our code looks like our data. I can read it from the reader, and I get back data structures in my language. Is that really all that there is to code? Is that really all that we care about? I want to talk about execution as data. What if the execution of my program itself were data? Well, then I could do all sorts of interesting things. Maybe I have a rule that is that's matching on a certain pattern, and I know what it's called. It's called my rule, and it has some variables. It's paying past some arguments. But for some reason, it's getting me weird results. And I have no idea what the hell arguments this thing is being passed, right? And you might be thinking, well, it's not that hard to go find your function. Yeah, unless it's deeply nested in some node module that I have no idea where it is, and I have to dive down there for an hour looking for it because it's dynamically generated. I'm not mad. So anyways, maybe I just want to say, hey, program, when you're executing things, if you see an expression called with my rule and 2 arguments, just print those arguments for me. Why can't I do that? This is just a hint. If my execution is data, I can pattern match on my execution and get out things that I want. Or maybe we want to go the other way around. I have some weird data, and I have no idea where this weird data is coming from. Please, program, as you're executing, if you see an expression and it results in some weird data, tell me what's causing this. Just print it out for me. Or maybe we have some error message. So every time I write a division in my program, I am just counting down until that division by 0 comes up. Right? It's the one division in my program. And so, boom, division by 0 on that line. Yes, it's my one division. And then it's oh, it's 5 divided by 0. Gave you some more information. Thank you. So this here, I've made a custom thing, which I actually could have fit on this slide. It's not that hard, but it would have been everyone staring and squinting at lots of dots. But here I've made my own custom operator called all steps between. And what I'm doing is I'm saying, find me in my execution history, because I can just save off. It's data. I can save it, right? The first instance of 0, and then all the steps in between until I have a division by 0, and return me back those steps. So now I can see, how did I get from one place to another? And I could have added, and 8 steps before that, because maybe that's more important. But we can talk about the execution history. Or maybe we can do even more. What if we could have scoped rules? So there was a talk at Strange Loop, I can't remember which year, but it was about idealized commit logs using code slicing that I thought was a really interesting talk. And the idea is, if you take a test, what if I could just find out all the code that was run just from that one test? I could understand every single part that that test is exercising very easily. Well, here we could say that, right? We could say, with execution rule, anytime you find any rule, just save it for me. And now I'll run my test, and I'll see all the rules that were invoked from that test. But this is not enough, right? If we have real data-oriented programming, we need rules as data. Our rules themselves should be data. So we can do things like this. We could say, hey, find me all the rules that contain print. Any rule that prints, I just want to know what it is, right? Or maybe we say, hey, I want to find all my deprecated rules. I know there's some deprecated rule. I just want to find everywhere where it is. And you have it in memory. I can just find all of these rules because my rules themselves are data, right? They're not just random text blobs in a file. They're data. Or maybe we want to find the deprecated rule, and we want to actually replace it. We want to say, hey, every call to my deprecated rule that has these certain arguments, replace it with my new rule and change the order of the arguments. Or finally, maybe we want to look at our rule history. Maybe the language itself knows about these rules and how they've changed over time, and we know that if code constantly is changing, that's probably where some bugs are, and we can say, find me any rule that's repeated 10 or more times. And like I said, I'm a pie-in-the-sky kind of person, and this is really cool, and I've made some little proof of concept here or there, nothing that I would actually show anybody because it's ugly. But maybe you're like, okay, yeah, that's cool, but what about something more immediate, more real, something you actually have some working code for, right? And I want to show one more example that we get out of this sort of model, and that's programming by example. So if you've seen Wilbert's Barleyman, it's this system that lets you write your unit tests, and then it figures out the code for you. And it does it by really cool stuff with Minicanner and writing a scheme interpreter in Scheme, and this big, nice tower of interpreters going on. And it's really interesting because you just write the test cases and you get out working code. But it takes quite a while. And if you mess up your test cases, as I did during a live talk, it can never return. Well, that's because trying to infer functional code is hard. There's a lot of moving parts going on. There's a lot of weird things. But what about trying to infer declarative code? So I've written one that doesn't handle everything, but it handles that first example, the hello world example that we talked about. And it's not in Meander proper, but I have it, and it really does work. And it's called infer rewrite. And you can hand it a single example of your input and your output, and it will give you back the exact code that we wrote before. And this is what we can get from a declarative data model, right? Yes, I haven't done repeats, I haven't done all sorts of things, but when we have a declarative data model where there's relationships between our code, and that's all our code looks like, this becomes deterministic. This becomes easy. There's these algorithms called anti-unification that they're opposite of unification, which is what pattern matching uses. And so you can use these things to spit out the patterns for you. Wouldn't it be great if at least that easy code that is boilerplate and annoying and I just have to retype all those names all the time would just be generated for me? I want to leave you with a thought. When we program and we look at someone else's code, it's opaque to us what's going on. Oftentimes we just get frustrated, like, what was this person thinking? This is just garbage. And then we look at the blame, and it's us. But it's opaque. If 6 months ago us wrote some code, we have no idea what it's doing because it's this series of transformations that in each of them they might be declarative, but when you combine them together, they're not. They're hard to think about. And so I think Meander is a really important step in this future. I think it's a really important exploration, a journey to try to find a way to have a more transparent future, where when you go look at code, you can tell what it's doing because it matches the data that it's transforming. And if programming is just data transformation, as I think a lot of people believe, why wouldn't we do that? Why wouldn't we talk about our data directly? So that's what I really want to leave you with. Not go use Meander, although go use Meander. But go make a more transparent future. Thank you very much.